in instrumentation and control engineering, having more than 22 years of teaching experience and specialization with weights and measures, electrical measuring instrument, circuit theory, and electrical machines. So it will be a wonderful topic for us to understand how the gas meters can be tested, calibrated, and verified. It is one of the very good thing that as the India is progressing fast, we need these type of instruments which are verified and stamped and accurate in their measurement. We have with us, thank you very much, Professor Pandey, to be with us, and I hope that this presentation will be very good today. We have with us with our Honorable Shri B.N. Dixit, our Director Legal Metrology, sir. Sir, thank you very much for being with us. I know that you are always with us, and your work in the field of legal metrology will always be remembered, whether it is in the advancement of the state legal metrology departments or the development of new RRSs. Thank you very much, sir. I would like to request you to kindly inaugurate this workshop. Over to you, sir, please.
Thank you, Sri Ashutosh Agarwal ji, Director Legal Metrology, Government of India, Dr. Vivek Pandey ji, Professor at ILM Ranchi, Indian Institute of Legal Metrology, Ranchi. Today it is the very burning topic, and one of the important of the gas meter is that how to manufacture it, how to calibrate it, and how to verify it. I think the government of India is very conscious about it. The lot of the manufacturer has got the approval of the gas meter. There is need that it should be manufactured in India, and uh, people may be benefited and employment may be generated throughout the country. And the research work should also be done in this very field, that how to design the gas meter and all that type of things. I hope that today program will be very successful, and Dr. Pandey lecture will be very beneficial to all the participants and the legal metrology officers who are joining this very field, and the various scientists who are joining this very seminars. And this is the very well work done of the director legal metrology, that every Saturday he is inviting various experts in this very field of the legal metrology, as well as the various other topics which are related with the consumers and the common peoples. The people are being well aware, and that very conscious uh, due to this very Saturday program. The participants are joining day by day in this very program, and that is very increasing there. And that ways where that we are also very thankful to Sri Ashutosh Agarwal, that uh, he has created interest of the consumer and the participant due to this Saturday series programs. So thank you to Director Legal Metrology. Thank you, Dr. Pandey. I hope that today's seminar will be very wonderful and all the people will be benefited. Thanks, everybody. Thanks.
Thank you, sir. Thank you very much for your kind and motivating words. Thanks a lot. Now, I'd like to request Professor Pandey to kindly deliver this talk. Over to you, sir, please.
So thank you so much, sir. First of all, a very good morning to our respected Director Legal Metrology, Ashutosh Agarwal, sir, who have provided me this another opportunity to speak as an expert on a topic, gas meter. Um, Before I start my presentation, I must congratulate Director Legal Metrology, sir, for this continuous webinar happening on each Saturday, and on various topics of metrology and legal metrology. And I would also like to thank our ex-director legal metrology, B.N. Dixit, sir, who always showers his blessings on me and other legal metrology officers. And he is always very supportive, and um, whenever we need some guidance in the field of legal metrology, he is always there. He never deny that right now I'm busy or some other engagements are there. He's always supporting us. So thank you very much, sir. Now, I would like to welcome all the participants who are joining this webinar. Um, Thank you for joining this webinar. I'm pleased to present today's topic on gas meters, which are essential device used to measure the consumption of gas in residential, commercial, and industrial sectors. Uh, as we all know that in the current scenario where the war is going on, so there is a lots of shortage of conventional energy resources, so out of which the gas is a very important one. So uh, just observing the current situation, we can feel that how much important it is to means measure the quantity of gas using the gas meters, and how we can means enforce the regulations of gas meter, which is recently notified in our legal metrology general rule 2011. So the current scenario actually increases its importance. So today we'll be discussing all the technological metrological aspect of this gas meter. Now we all know that accurate gas measurement is very important for fair billing, safety, and efficient energy management. And let me first share my PowerPoint presentation, then I will speak further. Uh, so we all know that by using the power of section 52 subsection 1 and 2, recently our uh, government of India notified this rule on gas meter in legal metrology general rule 2011, which is included in part 11 of 8th schedule in legal metrology general rule 2011. And this official gadget was notified on 21st of April 2025, and it came into the force on first day of September 2025. And most of the content of this regulation, which is notified in our general rule, is based upon international recommendation for gas meter, that is OIML R137. Today, in today's presentation, I'll be briefly discussed about the terminology related to the gas meters. I will also discuss the different types of gas meters which are basically used nowadays in the industrial as well as domestic applications. I'll also explain the metrological characteristic which determine the performance and accuracy of the gas meters. I will also cover the metrological requirement that ensures these meters meet proper standards. And finally, I will discuss about the metrological control in a you can say detailed manner, which will involve all the steps we follow during the verification procedure whenever a model approval is allotted for a gas meter. So what type of test we perform, and what are the requirements of those tests, so that I will be discussing. So let us begin with this presentation, everyone. Now, before I start the first part, that is the terminology of the gas meters, we should be knowing that this what if this gadget notification, which is recently came for this gas meter, uh, it is related to all those gas meters which are used for domestic gas supply system. That is, domestic gas meters are included. Industrial and commercial gas meters are covered under this regulation. As well as I also would like to tell you that it doesn't matter what type of technology is used in the measurement of quantity of gas. That means the gas meter can be based upon electronic technology, ultrasonic technology, turbine based gas meter, diaphragm based gas meters, or it might be rotatory type. all these technologies which are used in the gas meters are covered under this regulation. But yes, at the same time, we should also be knowing that the compressed natural gas dispensers, which are also there for and they are used for measuring the quantity of gas in the CNG supply. They are not covered under this regulation. They are having a different place in our rule. That is, it is already notified. And there is a liquefied gas meters multi-phase type, which is also not included under this regulation. Then steam or vapor phase flow meters are also not the part of this rule. Now, when I come to this first part of the presentation, that is called terminology. So here I would like to discuss some important terminologies which we should understand before we discuss about metrological parameters of the gas meters. The first terminology is related to the sensor part of the gas meter. We all know that a gas measuring instrument is what it basically measures the quantity of gas in terms of volume or in terms of mass with the help of combination of devices. So out of these devices, the first device, and you can say it is the heart of the any measuring system, that is called sensor. What it does, actually, it receives the you can say the a particular signal from the whenever a quantity of gas passes through the gas meter, it receives the signal, and it converts that signal in a form or in a such a form, so that we can further process that signal in a measurable form. That means we can convert the signal into a quantity of gas. Now, the second part is the measuring transducer, which is basically an electronic device which converts one form of the signal into other form. Mostly in case of gas measuring instrument, the flow of the gas is basically, which is the flow of the gas is what? It is a mechanical signal. So the flow of gas is converted into an electrical voltage. So this particular part is done or performed by the device which is called measuring transducer. The next part is the calculator. We know very well that the measuring transducer, when it will convert the input signal into the voltage pulses, so there should be some device which will count those pulses, which will store the number of pulses, and then and after storing those pulses, further it can be sent to upcoming devices, so that finally the quantity of gas can be or may be displayed on the display. Now, this calculation of the voltage pulses is done with the help of this calculator. Next part is the indicating or displaying device, which basically performs the display function of a gas meter. That means the final quantity of gas in terms of mass or volume will be displayed on this displaying device. Now here we should be knowing one thing, that if a printing device is there in the gas meter, so it will not be treated as indicating device. Basically, the printing device is treated as ancillary device of this gas meter functioning. Next one is the correction device. Regarding this particular part, I would like to tell you one thing, that gas is a kind of substance where the quantity of gas, if it is suppose measured in terms of volume, so that quantity of gas in terms of volume varies too much if there is considerable variation in temperature as well as pressure. So if the atmospheric temperature or the gas temperature or the gas pressure is changing, so it will affect too much in the quantity of gas measurement. So we should always install, or the manufacturer should always install, a correcting device inside the meter or the gas meter, which will perform the correction regarding the variation of these parameters. So suppose if suppose a gas meter is designed to perform the correct gas measurement at a temperature of say 15 degrees Celsius. So 15 degrees Celsius is the base temperature, suppose, of a gas meter. So it means whenever the gas at 15 degrees Celsius is transferring through that gas meter, it will perform the correct measurement of volume. But suppose the temperature of that gas is changing from 15 degrees Celsius, it becomes 17 degrees Celsius. So due to variation in this 2 degrees Celsius temperature in the gas, what will happen? The quantity of gas in terms of volume will change. That means the wrong measurement would be possible. So what should be there? There should be a correction device inside the gas measuring instrument, which can sense that temperature, that there is a variation in temperature. It is not equal to the base temperature. So whatever amount of variation is there, accordingly it should perform the correction, and it should always indicate the correct quantity of gas, whether the temperature is changing or whether the pressure is also changing or varying. Next part is the ancillary device. I just mentioned that the printing devices, the communication devices, the memory devices. Okay, so where we store the data. Suppose we are storing the number of pulses generated in the gas meter. We have to communicate those pulses so that it will be processed through a programming device, and finally the display will be there for the quantity of gas. So these intermediary operations are basically performed in the gas meter with the help of ancillary devices. So you can say that ancillary devices are nothing but what? They are the supporting devices for the gas measuring instrument. Now, the next part is associated measuring devices. I just mentioned that in all gas meters, there is a provision of correction device which performs the correction based upon the variation in temperature, pressure, and other parameters. So now, suppose there is a correction device. So correction device will perform the correction in the measurement on the basis of certain measurement of that you can say that the temperature or pressure. So I mean to say, suppose a correction device has to correct the volume corresponding to the actual temperature of the gas. Actual temperature is suppose 17 degrees Celsius. However, the base temperature is 15 degrees Celsius. The quantity of gas is to be measured at 15 degrees Celsius, but the actual temperature of the gas is currently now 17 degrees Celsius. Now, how the correcting device will be able to know that the temperature is 17 degrees Celsius? So for that, we should install a measuring device. That means a temperature sensing device should be installed inside the gas meter, which will sense the actual temperature or the operating temperature of the gas, and it will support in that correction of the quantity of the gas based upon the variation in temperature, as well as the similar kind of device for pressure also we can install. So this pressure measuring device, temperature measuring devices are what? They are associated measuring device. Now, there is a terminology called family of gas meters. So this is also a very important aspect that plays a very important role during the model approval. So suppose a manufacturer is manufacturing gas meters of different sizes and different specifications as well as different technologies. So the question is here that whether he should get model approval for only one of the design or only one of the model, or he should get all model approval for all different designs and specifications. So for that, we should always look for this family of gas meters. That means if a gas meter, there are number of gas meters where the manufacturer is same, where the geometric similarity is there in the measuring part, where the same metering principle is used. That means the gas meter, all the gas meters are supposed based upon turbine type gas meters, or they are rotatory type, or they might be of ultrasonic type technology. So whether this metering principle is same or not, then whether the Q max to Q minimum and Q max to Q transitional ratios are roughly same or not for the number of gas meters, then whether they are having same accuracy classes or not, whether the same electronic devices for each meter size are there or not, or where the design and assembly components are similar or not, whether the same materials for the components are used or not for all those number of gas meters which are submitted for the model approval or not. If all these are same or all these points are complying for those gas meters, so they will be treated as family of gas meters. That means only one gas meter can be checked for the model approval, and the model approval can be equally applied for all other meters. They don't need separate model approval, or they don't need separate verification, I must say. Okay, but yes, if there are different you can say measuring principle is used, or this q max to q minimum and q max to q transitional ratios are means very much different for different gas meters, and they are of different accuracy classes, so definitely the model approval should be performed on separate meters, not for only individual meters. Now, when we talk about the different types of technologies nowadays used in the gas meter, so one of the very important type of technology used in the gas meter is this ultrasonic type gas meter, mostly used for the industrial applications where the huge quantity of gas transaction is happening. So wherever the bulk quantity of gas transaction is happening, there this ultrasonic gas meters plays a very important role, because they perform accurate and precise measurement. It doesn't matter that whether the funnel diameter is more or it is small. Even if the funnel diameter is big, it can perform accurate measurement. Basically, what is there whenever we are talking about the mechanical type, or you can say the type of gas meter where internally there is a rotating part or moving part, uh, which rotates or moves during the measurement of quantity of gas. There, if you are increasing the bore size or the diameter size of the pipe, or the diameter size of the gas meter, then in that case the measurement will not be that much accurate. However, in ultrasonic meter it is very accurate, because there is no moving part inside. Okay, it is based upon ultrasonic principle. So here the principle is very simple, that an ultrasonic controller is there which controls the operation of two ultrasonic sensors, where one ultrasonic sensor is located at nearby you can say lower height, and other ultrasonic sensor is installed at little bit upper side or higher side. At little bit means you can say increased height. So whenever the gas is passing from bottom to top, you can imagine that whenever gas is flowing from downside to upside, and suppose the ultrasonic waves are traveling from ultrasonic sensor A to B, so obviously it will take less time to reach ultrasonic sensor B. And whenever ultrasonic waves are traveling from ultrasonic sensor B to A, so it takes more time to reach, because it has to flow against the flow of gas. It has to move against the gas flow, so it will take more time to reach to ultrasonic sensor A. And this difference of time is basically what it depends, it is directly proportional to the rate of flow of the gas which is passing through the funnel. And this difference of time is basically measured by that ultrasonic controller, and finally this difference of time is calibrated in terms of volume. So this is a very modern technology used for the measurement of quantity of gas. Another type of technology which is very common is called turbine gas flow meter, where a turbine type rotor is there inside the gas meter, and nearby that turbine you will see that there is a inductive coil. And in this turbine type gas flow meter, at the turbine itself or rotating wheel itself, there is a small magnet attached. So whenever the gas is flowing through this gas meter, what happens? Due to the pressure of the gas, this turbine rotates, and due to rotation of this turbine, actually that magnetic poles also rotate. Magnetic pole is also rotating, and whenever the magnetic pole is rotating, it means what? The magnetic field is rotating. And within the you can say region of this rotating magnetic field, if there is any conductor placed, so in that conductor, as per Faraday's law of electromagnetic induction, a small voltage is induced. Okay, so that voltage which is induced because of this rotating magnetic field is what? It depends, or it is directly proportional to the number of rotation made by this rotating wheel. And you know very well that the number of rotation made by the wheel is directly proportional to the gas flow, or the rate of gas flowing through the gas meter. So indirectly we can say that the voltage induced in the inductive coil is proportional to the flow rate passing to the, or the gas flow rate passing through the gas meter, and that is how we can calibrate further that voltage in terms of volume. So this was one technology. Then another very common technology is positive displacement meter gas, positive displacement meter type gas flow meters, where there are, you can see in the picture, the two oval shaped gears are there whenever the gas is passing through these oval shaped gears. So what happens that during the rotation of these oval shaped gears, a small chamber is created inside the gas meter, and in that small chamber, which is calibrated for a specific volume, or the you can say standard volume. Okay, so then that chamber is filled with the gas passing through the gas meter, and that quantity of gas trapped inside that chamber is what? It is fixed. It is in a fixed quantity. So suppose if I'm taking in this example that in the cavity which is created inside the gas meter due to rotation of the oval shaped gear is, suppose it is of it is having a volume of 100 ml. Okay, so this 100 ml cavity will be created, or 100 is ml space will be created between the oval shaped gears during the rotation two times, once in lower side of the meter, and another on the upper side of the this gas meter during the rotation. So we can say that in one complete rotation of these oval shaped gears, total 200 ml of quantity will pass through this gas meter. Okay, and yes, the number of rotation will be calculated by, with the help of a mechanical calculator, and then finally we can convert those number of rotation in the quantity of gas passing through the gas meter. More the gas is passing through the gas meter, that means more the flow rate, means more will be the number of rotation. So this is positive displacement meter technology. This is another rotary piston type gas meter. This type of technology is also very common in gas meters. So these are few examples I have given just to make you understand that different types of technologies can be there in the gas meters, and all those gas meters are covered under this our regulation. Okay, that is, which is recently notified in our rule. Now here one table is mentioned in our notified rule, which is basically indicating the period of verification and re-verification. Okay, so you can see that here for different types of gas meters like diaphragm gas meters, the initial verification should happen after 7 years, and the subsequent re-verification should happen after 5 years. Similarly, the rotary piston type 20 years, 17 years, then 6 years and 4 years for turbine gas flow meters. So these verification and re-verification periods are different here based upon the technology because of the reliability of the operation, how much reliable they are in terms of accuracy. More the reliable the instrument is there or the technology is there, means more will be the verification period. Okay, so this is how it is notified in our rule. Now, I am coming to the next part of the presentation, that is called metrological characteristic. And as I already told you that the metrological characteristic is nothing but what? These are some important parameters related to the measuring instrument, which plays directly an important role in the accuracy and reliability of the operation of the gas meter. So one of the such metrological characteristic parameter is what? Weighted mean error, a very important parameter which we usually calculate and determine for checking the accuracy of operation of any gas meter. Now this weighted mean error is what? It is basically a parameter which is indicating that how the error is distributed in the full flow range of the gas meter. That means if suppose a gas meter is designed for a certain range of the flow rate, like Q minimum to Q maximum flow rate. So this weighted mean error is a parameter which is basically indicating that if we are suppose trying to find out the error in the measurement of the gas meter close to minimum flow rate, then close to maximum flow rate, and then we are also trying to determine the error of the error in the accuracy of the gas meter at other flow rates between Q minimum to Q maximum. And suppose we have determined this error, say for 8 different flow rates, 8 number of different flow rates. So for all those 8 readings, whether this error is distributed in a uniform manner or not, that is basically we checked with the help of this parameter called weighted mean error. That means if it is uniformly distributed, then weighted mean error should be what within the prescribed limit as specified in our rule. Next important metrological characteristic is intrinsic error, which is again a very important parameter, and it is nothing but what, whenever we are trying to determine the error in the gas meter under reference condition. For all gas meters, a reference condition is specified by the manufacturer, and we use that reference condition to find out the intrinsic error of the gas meter. That means reference condition should be maintained in the laboratory, and then error will be determined for the gas meter, and that is called intrinsic error. Fault is nothing but it is the difference of error of any gas meter in normal operating condition and the error obtained under reference condition. So suppose a gas meter is there, we are testing that gas meter for its accuracy at reference condition, and we found some error. Okay, now the same accuracy test we are performing on the gas meter in normal operating condition without bothering about reference condition. So in normal operating condition, whatever error we are getting, and in reference condition, whatever error we have got, the difference of these two is called what? Fault. Now, in metrological characteristic, the next important parameter is base condition. As previously I mentioned about the correction factor or the correcting device. I told you that the volume of the gas changes significantly if there is variation in the temperature as well as pressure. So all the gas meters should be incorporated with the temperature correcting device, pressure correcting device, means those parameters which can change in the variation of which can change the accuracy of the measurement of the gas meter. With respect to those variations, the correction should happen. Now, for performing this correction in the measurement based upon variation in temperature or pressure, a manufacturer has to specify the base conditions. That means suppose a gas meter is manufactured by the manufacturer, so that manufacturer has to specify that what is the base temperature of that gas meter and what should be the base pressure of that gas meter. So if suppose base temperature is say 15 degrees Celsius, so it means at 15 degrees Celsius, if the gas measurement is taking place, so no correction is required, and it can show directly the indication, it can give you the direct indication of the volume. But suppose the temperature of the gas is changing, so based upon variation in temperature from the base conditions, the correction should happen, and regarding that, a correction factor must be specified. The next one is the rated condition. For all gas meters, some rated parameters are specified by the manufacturer with respect to the temperature, pressure, humidity, then your vibrations, the electrical parameters like voltage variation, okay, then frequency variation. So for all these, some rated parameters or rated ranges should be specified with respect to all these parameters by the manufacturer. Then reference condition, I just mentioned that some reference condition with respect to temperature, pressure and other parameters should also be specified by the manufacturer, which is basically used during the testing procedure. So whenever we test the gas meter, then we apply these reference conditions. Now the next important topic related to this gas meter is the operating condition. Now, when we talk about the operating condition, means in what condition the gas measurement is taking place. the quantity of gas is being measured. That means whenever a gas is passing through the gas meter, so what is the current temperature? What is the current pressure? What is the current specific density? What is the current humidity? So all these conditions, all these values of these parameters, temperature, pressure, and gas compositions are called operating conditions. Now, here the next three terminologies or the operating conditions which I am going to discuss is very, very important related to the operation of a gas meter. That is maximum flow rate, minimum flow rate, and your transitional flow rate. Now, we all know very well that whenever a gas is passing through the gas meter for the measurement purpose, then gas passes through the gas meter at a certain flow rate. Now, this flow rate, whenever it is changing, suppose gas meter is measuring the volume of the gas, and the gas flow rate is suppose changing during the measurement process. So whenever it is changing, then accuracy of the gas meter also changes. So based upon this, every manufacturer specifies the minimum and maximum flow rate. That means a minimum flow rate below which if the gas will pass through the gas meter, then accuracy is not assured. That means the gas through the gas meter, the gas should always pass above the minimum flow rate. Similarly, there is a maximum flow rate specified. That means above maximum flow rate, the accuracy is not guaranteed. That means accuracy is only limited or assured up to the maximum flow rate specified by the manufacturer. Now, within this minimum to maximum flow rate, also you should be knowing that the accuracy or the amount of error observed during the measurement of quantity of gas changes. Whenever gas is passing through the meter at minimum flow rate, error might be different. And whenever gas is passing through the gas meter at maximum flow rate, it might be different from the amount of error which it was showing at minimum flow rate. So as we know that the error, the amount of error is changing from minimum to maximum flow rate. So obviously during the testing procedure, the maximum permissible error or the tolerance specified for this accuracy of gas meter should be different for different ranges. What I'm trying to say that yes, a gas meter can function accurately between minimum to maximum flow rate, but between minimum to maximum flow rate also there is a reason where the accuracy of the gas meter is basically changing, and that particular borderline is called transitional flow rate. So this transitional flow rate is nothing but a specific flow rate which basically divides the complete flow range of the gas meter into two zones, okay, upper zone and lower zone. So upper zone means transitional flow rate to maximum flow rate is called upper zone or upper flow rate zone for the gas meter. That means within this flow rate, if we are operating the gas meter, the amount of error might be different, or it should have a different tolerance or different MP. And if we are operating our gas flow meter within the range of minimum flow rate to transitional flow rate, so accuracy of the gas meter will be different. So definitely if accuracy is different, so tolerance must also be different. Now, the next operating condition is the working temperature. That means the normal operating temperature of the gas. That means whenever a gas meter is connected with the gas supply line and the gas is passing through the gas meter and the measurement of gas is taking place, so what is the temperature at that time? That is called working temperature. Then a manufacturer also specifies the minimum and maximum working temperature for the gas meters, T minimum to T maximum, and the gas meter must be operated within these two temperature ranges, that is minimum to maximum temperature, so that it can perform the correct measurement of the quantity of the gas. And if it is going means the gas temperature is going beyond this range, that means accuracy might be affected. Similarly, there is a specified temperature range. Now, specified temperature is also specified by the manufacturer, and it is nothing but it is somewhere between the minimum and maximum temperatures. Minimum and maximum temperature, between minimum and maximum temperature, there is a specified temperature range, and actually this minimum and maximum temperature ranges are specified or determined with the help of this specified temperature. Means above specified temperature at a certain value there will be a maximum temperature, and below specified temperature a manufacturer will specify at a certain difference, it will specify the minimum temperature. Next one is the working pressure. That means whenever a gas measurement is taking place through the gas meter, so what is the actual pressure of the gas at that time? That is the gas pressure. Manufacturer will also specify a minimum and maximum pressure ranges for the gas meter. So a gas meter should be operated within the specified gas working pressure ranges. And there is a static pressure loss in the gas meter. We all know very well that whenever gas is passing through the gas meter, so at inlet side the pressure will be little bit high, and outlet side it will be little bit dropped. Pressure will be little bit decreased at outlet side because of that measuring instrument. Okay, so difference of this inlet side pressure of the gas meter and outlet side pressure is called what? Static pressure loss. And our this metrological characteristic and of this regulation is saying that the difference in pressure loss should not be too much in case of a gas meter for accurate measurement. If it is very high, that means the accuracy may be affected. Then working density, that means what is the density of the gas in the gas meter corresponding to working pressure and the working temperature. Working density means it is the ratio of mass per volume of the quantity of gas. Now the next part of this presentation is meteorological requirement. As I already said to you that there are certain meteorological requirements prescribed in our rule by our Ministry of Consumer Affairs, who have notified this rule. So they have specified the meteorological requirements for the gas. And in this table, you can see that all those meteorological requirements are mentioned. Like the first requirement is related to the ambient temperature. Ambient temperature means the temperature under which the gas meter is functioning. So you can see that here in ambient temperature, there is a lower temperature, lower temperatures are mentioned, and high temperature ranges are mentioned. So what is the meaning here? The meaning is here the meteorological requirement is saying that whenever a manufacturer will design a gas meter, so he will specify the temperature range following these ambient temperature ranges. That means the lower temperature range, he can select any one value from these which is specified in this table. That means he can specify the minimum temperature as minus 40 degrees Celsius, or he can specify the minimum temperature as minus 25, minus 10 degrees Celsius, 0 degrees Celsius, or 5 degrees Celsius. Similarly, he can specify a higher temperature or the maximum temperature as 30 degrees Celsius, 40 degrees Celsius, 55, 65, or 70 degrees Celsius. But here one thing is to be remembered that whenever manufacturer is specifying the minimum and maximum temperature range, he can choose the values from this table, but yes, during the selection of the values, he should ensure that the minimum difference in minimum to maximum temperature range should be 50 Kelvin or 50 degrees Celsius. What I'm trying to say, that if suppose a certain manufacturer has specified the minimum temperature for a gas meter as 5 degrees Celsius. Okay, so 5 degrees Celsius, if it is a minimum temperature, so maximum temperature cannot be 30 degrees Celsius. It cannot be 40 degrees Celsius. It should be minimum 55 degrees Celsius. Okay, so that it can maintain a gap of how much? 50 Kelvin or 50 degree Celsius. So that is the requirement of our gas meter regulation in terms of temperature. Now, similarly, there is a meteorological requirement related to the humidity part. That means manufacturer will specify at least 93% of humidity level for the gas meter functioning. That means accurate functioning of the gas meter. Similarly, the atmospheric pressure range is specified in kilopascal. Similarly, the vibration range is specified. DC main voltage as specified by the manufacturer. AC main voltage. I was also telling you that not just environmental or climatic parameters are responsible for the correct measurement. We should be knowing that electrical parameters are also playing very important role whenever the measurement of quantity of gas is taking place with the help of an electronic type gas meter. So if a gas meter is there which is supplied by an alternating voltage AC supply, okay, in our country the nominal AC supply voltage is usually around 240 volts. So suppose 240 volt single phase supply is connected with the gas meter, okay. So the metrological requirement is saying that the gas meter can operate at 240 volt supply, which is what, which is the standard voltage supply, but voltage supply may deviate or may fluctuate also. So it can vary between 240 minus 15% to 240 plus 10%. That means 15% lesser voltage supply if it is given to the gas meter, okay, up to 15% less of 240 volt supply is given to the gas meter, then still it will work accurately. And if the supply voltage is given more than 240 volt but up to a 10% of hike, then also it will perform the correct measurement. Similarly, the supply frequency. In our country, we all know that AC supply system is having 50 hertz supply frequency. So 50 hertz supply frequency means here the range is specified like 50 minus 2% and 52 plus 2%. That means what? 2% of 50 hertz is what? 1 hertz. That means whenever an AC supply is connected with the gas meter, so AC supply frequency may vary between 49 hertz to 51 hertz. So if the supply frequency is going below 49 hertz, so accuracy might be affected. And if the supply frequency is going above 51 hertz, again this accuracy of the gas meter may be affected. So we should all we should very carefully observe these parameters during the functioning of the gas meter, whether it is connected for the domestic applications or the industrial applications. So these are the some metrological requirements specified in the table. Now the next metrological requirement is related to the flow rate. I specified or I discussed 3 flow rates to you people just 2 slides back. Maximum flow rate, minimum flow rate, and transitional flow rates. I told you that these flow rates are specified by the manufacturer, but manufacturer also cannot specify any value of transitional flow rate, minimum flow rate, and maximum flow rate. There is a guideline in our rule that whenever a manufacturer is specifying a maximum and minimum flow rate and transitional flow rate, so this table should be complied. So I have taken here an example to make you understand. Suppose a gas meter of model this Raychem is there, and I have taken from the Google search engine. So and suppose for this particular gas meter, manufacturer has specified the maximum flow rate of 22,500 liter per hour, minimum flow rate of 100 liter per hour, and transitional flow rate of 500 liter per hour. Okay. Forget about that overload flow rate. I will discuss about it later on. But if you will carefully see this maximum, minimum, and transitional flow rate, so what is the ratio of maximum and minimum flow rate here? It is 2,500 divided by 100, that is 25. Okay, so ratio of maximum to minimum flow rate is 25, and in above in the table which is shown in this slide, you can see that the Q max to Q minimum ratio, if it is between 5 to 50, which is in this case it is 25, so it is between 5 to 50, fine. So Q max to Q transitional ratio should always be more than 5. should be greater than or equal to 5. And in this case, the manufacturer has specified the transitional flow rate as 500 liter per hour. So if you will find out the ratio of Q maximum and QT, so you will find that Q maximum to QT ratio is coming as in this case it is 5. Okay, so it is 5. So it means what? It is complying this table. So this declaration is what? It is correct. That means maximum flow rate can be 2500, minimum flow rate can be 100 liter per hour, and transitional flow rate 500 liter per hour. It is satisfying this metrological requirement as per our regulation. Now, the next important aspect of the gas meter as per our regulation is what? The accuracy class. There are different accuracy classes for the different types of gas meters based upon its accuracy of measurement. And you know very well that accuracy totally depends upon what type of technology, means what quality components are used inside the gas meter for the measurement of quantity of gas, how much how accurately the ancillary devices or correcting devices are functioning inside the gas meter. Based upon these, actually this accuracy of the gas meters are specified, and depending upon its accuracy, the accuracy classes are specified by the manufacturer. And there are 3 accuracy classes which must be specified on the gas meters. It can be 0.5, it can be 1, it can be 1.5 as per our regulation. So there shouldn't be any other accuracy classes, only 3 accuracy classes as per our regulations. Any one of these accuracy class should be specified on the gas meters. Based upon different accuracy classes of the gas meters and different flow rates, the maximum permissible errors or for the accuracy of the gas meters are specified in this table 2 of this regulation. You can see that here this maximum permissible error limits are specified for 2 conditions. One, during model approval and initial verification, and another condition is during re-verification and inspection. And you can also see in this table that the maximum permissible errors in terms of percentage are different for different accuracy classes, and it is also different for different flow rates. As I recently mentioned you that there is a transitional flow rate in between minimum and maximum flow rate. So this transitional means what? Transitional means transition of accuracy. So there is a transitional flow rate in between maximum and minimum flow rate, where the accuracy value or the accuracy level of the gas meter changes. So based upon this, actually here the tolerances are different. So you can see here that for a certain flow meter, gas flow meter, minimum flow rate to transitional flow rate, where transitional flow rate is not included. Minimum flow rate to transitional flow rate, the MP during model approval is 1%, plus minus 1% for 0.5 accuracy class. It is plus minus 2% for 1 accuracy class, and it is plus minus 3% for 1.5 accuracy classes. However, during re-verification, the values are what? Twice the MP specified during model approval. But if suppose that gas meter is tested or it is checked during verification or during inspection at a flow rate which is equal to or more than the transitional flow rate, that is QT to Q maximum. So if flow rate of the gas meter is QT to Q maximum, then this maximum permissible error for different accuracy classes are what? They are different. You can see that the MP is what? It is plus minus 0.5% for same 0.5 accuracy class instrument if the flow rate is what? Above transitional flow rate. Okay, so if you can say that when the flow rate is increasing, so the percentage of MP is decreasing. Okay, so plus minus 0.5% for upper zone of the flow rate, and plus minus 1% for lower zone of the flow rate, and it is for accuracy class 0.5. Now here one thing I'd like to discuss which is very important, that is related to the same thing, this tolerance part, that whenever we are performing the testing of a gas meter, we should not only consider the flow rates for determination of the tolerances. That means the table is indicating that minimum to transitional flow rate, the MP is plus minus 1%. Transitional to maximum flow rate is plus minus 0.5% for 0.5 accuracy class. But we also know that accuracy doesn't change only with the variation in flow rate. It is also affected by the other parameters. Like if temperature is suppose changing, so accuracy will be changed. I told you that due to variation in the temperature, the volume of the gas changes. Fine. So, and I also told you that in all the gas meter, a correcting device is there. So during the testing of the gas meters, which are incorporated with the correction devices, whenever we are performing the accuracy test, we should be knowing one thing, that the tolerances will not be only that much which is specified in the table. Actually, the tolerances will be increased due to variation of the temperature, or for a different temperature of the gas. Means, suppose for a gas meter, there is a specified temperature. Let me tell you from by taking an example. A manufacturer has a specified specific temperature, or a specified temperature defined by the manufacturer is what? It is 20 degrees Celsius for a gas meter. So specified temperature is 20 degrees Celsius. Okay. And the table 2 I have just shown you is indicating, suppose we are taking the example of a certain gas flow meter, and for that, suppose maximum permissible error between QT to Q maximum is plus minus 1.5%. Now, whether during the accuracy test of that gas meter, which is also included with the temperature correcting device, whether the MP should be plus minus 1.5% or not, that we are discussing here. Actually, if the specified temperature is 20 degrees Celsius, okay, and suppose your operating temperature is also 20 degrees Celsius, manufacturer has specified the specified temperature as 20 degrees Celsius, and actually the gas temperature which is passing through the gas meter is also 20 degrees Celsius. So our regulation is saying that for a specified temperature of 20 degrees Celsius, the range of 5 degrees Celsius to 35 degrees Celsius. How we have got that? 20 degrees Celsius specified temperature plus minus 15 degrees Celsius. So if you will calculate 20 degrees Celsius plus minus 15 degrees Celsius, so it is the range of 5 degrees Celsius to 35 degrees Celsius. What does it mean? It means between 5 degrees Celsius to 35 degrees Celsius, if the gas temperature is there, so it means the tolerance which is specified in table 2 will be increased by plus 0.5%. That means the table is saying that for a range of QT to Q maximum, the MP is 1.5%. But because of the temperature of the gas is also changing, it is not at the base temperature. Okay, so we should provide more tolerance. We should provide more MP. So what is there? From 5 degrees Celsius to 35 degrees Celsius in this example, actually MP is not 1.5%, it is 2%, plus minus 2%. So 0.5% must be added because of the variation of temperature, because of the temperature correction factor. Now suppose the gas temperature which is passing through the gas is 35 degrees Celsius. Okay, it is increased to 35 degrees Celsius. Specified temperature is 20 degrees Celsius, but the actual temperature of the gas is 35 degrees Celsius. So still you can see that it is the range, it is in the range, that is 5 degrees Celsius to 35 degrees Celsius. So within this range, the operating temperature is there. So MP can be 1.5% plus 0.5%. That means whatever MP was there for 20 degrees Celsius, the same MP is there for 35 degrees Celsius. But suppose the temperature is further changing. Now the temperature is increased to 40 degrees Celsius. So you can see that it is now going beyond the range. That means T specified plus minus 15 degrees Celsius range is not covering this 40 degrees Celsius temperature now. Okay, so what is there? Our regulation is there saying that if the operating temperature is more than the range specified by 10 degrees Celsius, then 0.5% tolerance will be, sorry, yes, 0.5% tolerance will be further added. So within the range of 5 degrees Celsius to 35 degrees Celsius, it was 2%. It was increased by 0.5%. But above 5 degrees Celsius to 35 degrees Celsius, that means if we are further increasing it by 10 degrees Celsius on both sides, that means 10 degrees Celsius minus, that means minus 5 degrees Celsius to 45 degrees Celsius. So minus 5 to 45 degrees Celsius, the MP will become 2.5%. That means it is further increased by 0.5%. Okay. So that is how actually the tolerance should be used during the checking of the gas meter or during the verification or testing of the gas meter. Now the next part is related to the weighted mean error. As I already mentioned you that weighted mean error is nothing but it is indicating the distribution of error throughout the flow range of the gas flow meter, and it should be within the specified limit. And what is that specified limit? Specified limit is there in this table number 3. You can see that the weighted mean error should be plus minus 0.2% for accuracy class 0.5. It should be plus minus 0.4% for accuracy class 1. It should be plus minus 0.6% for accuracy class 1.5. And you can also note one thing here, that weighted mean error should not be calculated or should not be determined for any gas meter during re-verification and inspection. Means weighted mean error is only to be obtained during initial re-verification, initial verification and model approval. Okay. I will discuss a particular example at the end of the presentation to make you understand that how we will determine this weighted mean error. Error determination is very simple. We have to compare only the indicated volume of the gas meter with some reference quantity, and we will get the error. But weighted mean error needs little calculation, and that I will discuss with you with the help of an example. Now here in metrological requirement, another thing which I would like to discuss is the repair and damage of seal. Suppose a gas meter is installed for the transaction purpose. It is re-verified. Okay, it was re-verified. It was having the model approval. Means all the meteorological regulations were was followed for the gas meter. Okay. Now suppose the gas meter which is used for the transaction purpose, after a certain testing or during the functioning, we found that, or the user suppose found that the gas meter needs some repair or maintenance. It needs to be changed with some certain component inside the gas meter. Some certain component of the gas meter needs to be replaced. Okay, so we should be knowing one thing, that whenever a gas meter is repaired, that means any particular component is changed, or suppose the seal of the gas meter is broken. The seal means what? The seal applied by the legal metrology officers, the legal metrology authority. If seal is broken or any particular part is replaced, of any particular component of the gas meter is changed, so all the regulations related to the initial verification will be applied on that gas meter. That means after repair of the gas meter will be tested as per the requirement of initial verification. That means the first verification. Okay. And suppose the seal is also broken. So what I'm trying to say, that you have observed that in the table the tolerances are different.
Panditji, your voice is not there.
I'm sorry, sir. It
Please,
was
please.
it was a technical glitch.
Okay, no problem. Please continue. Please continue.
Yes. So what I was trying to say that during repair and damage of seals, suppose the gas meter is recently repaired or some component of the gas meter is changed, or the seal was damaged, then in that particular situation, the legal metrology officials should apply the metrological requirements for initial verification of the gas meter during the testing procedure. So if after repair, it needs to be tested again. So during testing procedure, actually MP of initial verification will be applied if it was repaired, okay, not re-verification MP. So this is an important aspect we should be knowing, which is mentioned in our gas meter regulation. The next part is related to the temperature, a very important parameter, because as again and again I am saying that due to variation in the temperature, the quantity of gas measurement can be affected. Here we should know one thing, that if the ambient temperature differs by the temperature of the gas for more than 20 degrees Celsius, the tolerance will become double. That means MP will be double. Example, suppose your gas meter, which is connected in any industrial application or the domestic application, suppose the gas which is passing through the gas meter is having a temperature of 15 degrees Celsius. The gas temperature means working temperature of the gas is what? It is 15 degrees Celsius. But outside the gas meter, the surrounding temperature or the atmospheric temperature where the gas meter is installed, okay, so that location, the surrounding ambient temperature is, suppose it is 40 degrees Celsius. So you can see here that the difference of gas temperature and the ambient temperature or the surrounding temperature is what? It is more than 20 degrees Celsius. Okay, so in this condition, if you are testing your gas meter, that means if the surrounding temperature is 40 degrees Celsius and the gas temperature is 15 degrees Celsius and you are performing a test on the gas meter, so MP will not be as specified in the table 2. MP will be double of the MP which is specified in the table. So if the MP is specified in the table is 1%, actually you have to consider 2% of MP, because of the same reason that gas measurement is affected very much whenever the temperature is changing. Next important metrological requirement is related to reproducibility, and this reproducibility is nothing but what it is basically the one kind of test we perform on a gas meter to check whether it is reproducing the result again and again identically or not. That means if a gas meter is there, we are operating that gas meter at minimum flow rate, okay, and we have performed the measurement and we compared the reading of the gas meter with some reference quantity or reference value, and we found some error, that there is a certain error in terms of percentage. Now we are performing the same accuracy test on the same gas meter, but at a different flow rate. We are increasing the flow rate from minimum flow rate to, suppose, transitional flow rate. And at transitional flow rate, we are testing it. And after performing the accuracy test, we found that error is now changed little bit. We compared the indication of the gas meter with the reference quantity again at a different flow rate, and we found that error is now in at this time the error is suppose different. Again we are doing the same test at a different flow rate in the same way, and we found a different error value. So that is how, suppose we have got or we have determined 6 different errors at 6 different flow rates, and here whenever we are performing the reproducibility test on the gas meter, we should be knowing one thing, that the reproducibility test is always performed at a flow rate of more than transitional flow rate. Okay, so that means you can say that the reproducibility test is to be performed at upper flow rate zone of the gas meter. So between QT to Q maximum, we can perform the test six times at 6 different flow rates, and all the errors which we are getting, we will see that out of those 6 errors, the difference in maximum error and minimum error should be less than or equal to 1/3 of the maximum permissible error. So if it is like that, then we say that its reproducibility characteristic or requirement is what? It is good for the gas meter. Repeatability is another methodological requirement of the gas meter, in which what we are doing, that we perform the test on a gas meter at same flow rate in same condition without changing any of the operating conditions. That means the temperature, pressure, humidity, by maintaining these parameter constant and also maintaining the constant flow rate. Suppose we are trying to find out error in accuracy of the gas meter at 3 times, at same flow rate 3 times. So the difference between maximum and minimum error of the gas meter should not be more than 1/3 of the maximum permissible error. And if it is there, then it means the consistency of the gas meter is what? It is good. It is consistent. Next methodological requirement is related to the durability part. That means a gas meter should meet the accuracy requirement related to the durability test. To perform this durability test, our rule is saying that the gas meter should be operated for a period of 2000 hours. At what flow rate? At a flow rate between Q 0.8 times of Q maximum to Q maximum. So suppose a gas flow meter is specified with the maximum flow rate of 2500 liter per hour. So 0.8 times of 2500 liter per hour is 2000 liter per hour. So that means between 2000 liter per hour to 2500 liter per hour, at any flow rate, we have to operate the gas meter continuously for 2000 hours. And after 2000 hours, then what we have to do? The same gas meter will be tested for accuracy. That means we will perform the accuracy test on the gas meter after 2000 hours, and we will see that whether the difference of the indicated value and the reference quantity is within the prescribed limit or not. If it is within prescribed limit, it means what? This gas meter has passed the durability test. It is durable. Similarly, there is another important test is related to the gas meter, which is called overload flow rate test. Overload flow rate test means suppose we are operating our gas meter above maximum flow rate. Q maximum, Q minimum to Q maximum is the flow rate which is specified by the manufacturer and certified by the legal metrology officers or authorities, to ensure that within these flow range, if the gas meter is functioning, then the accuracy will remain intact. But suppose a gas meter is operating above maximum flow rate, so whether it can sustain its operation or whether it can sustain with its accuracy or not, that is basically checked with the help of overload flow rate test. That means the same example, if I'm taking, suppose of overload a particular gas meter is there where the maximum flow rate is suppose specified as your 2000 liter per hour. So for this gas meter which is specified with 2000 liter per hour maximum flow rate, we have to perform overload flow rate test at 1.2 times of Q maximum, that is 2400 liter per hour flow rate we will apply on the gas meter. Through that gas meter, we will pass the gas at a flow rate of 2400 liter per hour. However, the maximum flow rate is only 2000 liter per hour, and we will do it for 1 hour continuously. Means at a very high flow rate as compared to the maximum flow rate. We will pass the gas for 1 hour, and after passing it for 1 hour, then we will again do what? We will perform the accuracy test of that gas meter within the specified range, and we will compare the result with the maximum permissible error, and we will also try to measure the fault. I told you that what is the fault? Fault is what? Fault is the error in difference of error in the normal operating condition and the error obtained in the reference condition. So that fault value should be less than or equal to 1/3 of the maximum permissible error. So these two things we will check to confirm whether at overload flow rate the instrument can maintain its accuracy or not. Next metrological requirement is related to the resolution of the gas meter, where our regulation is saying that the resolution or the least significant digit to measure the quantity of gas passing through a certain gas meter should not exceed the quantity of gas passed during 1 hour at minimum flow rate. Example: suppose a gas meter is there, and in that indication of that gas meter, you are finding that the gas meter indication in kiloliter digits are also there, in liter also digits are there, in milliliter also digits are there, fine, in the same display. So here we are talking about the minimum significant digit. That means suppose milliliter is the minimum significant digit. That means say 20 milliliter. So if 20 milliliter is the minimum significant digit, so whether this 20 milliliter significant digit is correct as per this regulation or not for a certain gas meter or not, that also can be checked. And for that, the rule is what? The value of least significant digit should be what? Less than or equal to minimum flow rate is specified for the gas meter into 1 hour. Example: suppose for a certain gas meter, the minimum flow rate is 0.016 meter cube per hour. Okay, 0.016 meter cube per hour. Now we all know that 1 meter cube is 1 kiloliter. So if we want to convert this into in liter, so it will become 16 liter per hour. Okay, so 0.016 meter cube per hour is suppose minimum flow rate is specified, and the display of the gas meter is having the least significant digit of 0.01 meter cube. If least significant digit is of 0.01 meter cube, so whether it is according to our metrological requirement or not for that gas meter, that we should check. And the calculation is saying what? As I told you that if minimum flow rate is given, you simply multiply it by 1 hour. So if you are multiplied in this example 0.016 meter cube per hour with 1 hour, so it will become 0.016 meter cube. So 0.016 meter cube is what? This is the maximum allowed resolution for this gas meter. Means whenever we are trying to define the least significant digit for the indication of this gas meter, so it should be equal to 0.016 meter cube or less. We cannot define in this particular gas meter, the least significant digit cannot be 0.02 meter cube because of the minimum flow rate. So in this case, the display has been specified by 0.01 meter cube resolution. So according to this calculation, it is what? It is correct. So 0.01 meter cube least significant digit is correct for this gas meter. Now, pulse generator, it is one of the component inside the gas meter which generates the number of voltage pulses based upon the quantity of gas passing through the gas meter. Here, regarding this pulse generator also, there is a regulation that if any gas meter is there where the manufacturer has given the marking regarding the number of pulse generated by the gas meter, means manufacturer is specifying, or he has specified on the specification data that the number of pulses generated by this gas meter is this much. So suppose on the label of the manufacturer, it is written like 1 pulse is equal to 10 liters. This is the specification provided by the manufacturer. So legal metrology officers should also verify this during the model approval checking. How we will verify it? We will pass certain quantity of the gas through the gas meter, and during the passing of that gas through that gas meter during model approval for this pulse generator testing, we will count, or we will you can say measure the number of voltage pulses using some device, some standard device which can measure the number of voltage pulses. So as for this, in here I have taken an example to make you understand that suppose for a particular gas meter, the it is specified like 1 pulse is equal to 10 liters, and we are trying to perform the pulse generator test, and for that we have decided that we will circulate 1000 liter, or we will transfer 1000 liter of the gas for the testing for this particular test. So after passing this 1000 liter of gas, a standard pulse generator has counted the number of pulse as 99.98. We monitored the number of pulses generated during the transfer of this 1000 liter of the gas to the gas meter, and we found that the average number of pulses generated by this gas meter for 1000 liter of gas passing through it is 99.98. So measured number of pulses by the gas meter is actually how much? It is 1000 divided by 99.98. That means the measured pulse is what? 10.002 liter. However, manufacturer is specified that it should be 10 liters. Actually, it is coming as 10.002 liter. So after comparing these two values, standard value is 10 liters, measured value is 10.002 liters. So comparing these two, we found that there is a percentage error of 0.02%, and our regulation is saying that if the pulse number of pulse generated for a certain quantity of the gas is mentioned by the manufacturer, and in that case, if actually during the test the number of pulses generated is having an error, and that error is within 0.05%, then it is okay. Otherwise, it means the pulses generated by the gas meter is not correct. It is not correctly indicated. Now, during the verification process of the gas meters, whenever we are performing the accuracy test of the gas meter, then during the verification part, we have to decide that at what flow rate the accuracy must be checked. So it is well understood that if a certain gas meter is specified from minimum flow rate to maximum flow rate, so throughout the flow range, the gas meter must be tested. Now, throughout the flow range, there can be n number of flow rates. How we will decide that at what number of flow rates and at what flow rates the accuracy test is to be performed. For that also there is a regulation specified in our rule. Here you can see that a formula, a logarithmic formula is given, log based formula is there, where n is given as 1 plus 3 log of q max to q minimum, q max divided by q minimum. Here n is what? N is basically the number of flow rates required for the testing, or you can say the number of testing points for the accuracy test of the gas meter. How many test points should be there between minimum flow rate to maximum flow rate? That is n. So how we will calculate it? Actually, it is based upon the ratio of q max to q minimum. And number of test point we can calculate using this logarithmic formula, but we have to also decide that suppose number of test points are 6. So what will be those 6 points? Minimum to maximum flow rate, that means one test, suppose we are performing at minimum flow rate. So after that minimum flow rate, which flow rate we have to choose? What will be the value of that flow rate? So that flow rate actually calculated with the help of second formula given in this particular slide, which is Qi is equal to cube root of 10 to the power 1 minus I into Q maximum. Now, how we will use these two formula or these two equations, that basically is explained in this particular example I have taken. You see here, suppose for a certain gas meter, the maximum flow rate is specified as 100 meter cube per hour and minimum flow rate is specified as 1 meter cube per hour. Okay, I have taken this simple example so that we can perform the calculation easily. So this Q maximum to Q minimum ratio here is what? It is 100. And we know very well that log to the base 10 of 100 is how much? If we calculate it, it is 2. So it means the overall value is 1 plus 3 into 2. And finally, we will get it, and we will get n as what? It is 7. That means 7 number of test points should be there for this particular gas meter during the testing process. 7 test points we have to choose. Now those 7 test points will be having what flow rates, that is calculated using the second formula. And the second formula is this one. Qi is equal to cube root of 10 to the power 1 minus I into Q max. As in the previous example, n was 7. So n was 7 means here it is mentioned in this formula that I value of this formula can vary from 1 to n minus 1. That means 1 to 6. So here for this particular example, I will be varying from 1, 2, 3, 4, 5 up to 6. Now, if suppose we are taking I as 1, first value we are choosing, first test point we are trying to define. So if I is 1, so here we can say that we can see that cube root of 10 to the power 1 minus 1, that is, it is cube root of 10 to the power 0 and it will be calculated as 1. So 1 into Q max is what? It is Q max. It means first test point Q1 is what? It is Q max. So 100 meter cube per hour is what? It is the first test point. Second test point will be what? Suppose we are applying I is equal to 2. So for I is equal to 2, this cube root of 10 to the power 1 minus I will become what? 1 upon cube root of 10. And 1 upon cube root of 10 is basically, if you will calculate, you will find it is 2.154. So Q2 will be what? Q maximum upon 2.154. So Q2 is coming as 46.4 meter cube per hour around. Similarly, third test point, if we are calculating, it will become 46.4 further divided by 2.154. So that is how we will get different points. So as you can see that I have told you that how many test points will be there? 7. And what will be those flow rates? From minimum to maximum flow rate, this is how we decide that minimum flow rate, then 2.15, 4.6, 10, 21.5, 46.4 and 100. These are calculated as per the requirements of our rule. So we use those two very important formula to decide these test points, at what test point we have to perform the test. And then we can set up these flow rates during the accuracy test, and we can compare the indicated value with the reference quantity to find out the percentage error, and then percentage error may be compared with the MP prescribed in table 2 and WME prescribed in table number 3. So these are the basically requirements. Now I am, because the time is less, so I am directly coming to that another part which I mentioned that I will be telling you that how we calculate the WME, weighted mean error. So to make you explain, actually I have taken this generalized block diagram which is treated here as a testing setup. This is not the actual testing setup, but yes, actual testing setup should look like this. You can see that in this particular testing system, there is a gas meter under test, which is connected with a pressure measuring device, temperature measuring device. Then there is a reference gas meter, standard gas meter, which should follow the traceability of our standard in our country. So using this particular testing setup, suppose we are performing the test of the gas meter, and suppose we are following the same funda. I told you that we have to decide the number of test points. So suppose the test points are, say there are 5 test points we have decided. Okay. And those 5 test points are what? Those 5 test points are Q minimum, 0.2 times of Q maximum, Q transitional, 0.4 times of Q maximum, and Q maximum. So for a certain flow meter, whenever we are performing the test at these flow rates, so actually what we have to do, we have to set up these flow rates with the flow control devices, and we will pass the gas at these flow rates to check the indicated volume in the gas meter under test, and we will also see the indicated volume in the reference gas meter. So as you can see here that the reference volume is mentioned here in the 3rd column of the table, and the meter volume, that is the gas meter under test volume, is mentioned in the 4th column. So comparing these two, we have got the errors, percentage error at different flow rates. So at 5 flow rates, we have found 5 different percentage of errors. These were the percentage of errors. Now using these percentage of errors, how we will calculate WME? WME is basically that formula I have shown you previously. This formula. WME is summation of KI EI divided by summation of KI, which says that suppose I is 1. So it means WME is equal to K1 E1 plus K2 E2 plus K3 E3 plus K4 E4 divided by K1 plus K2 plus K3 plus K4. And K1, K2, K3, K4, how we will get? We will get using the second part of this formula, that is Ki is Qi upon Q max if Qi is less than 0.7 times of Q maximum, or 1.4 minus Qi upon Q maximum if it is in this range. So following these two formulas, basically we have I have performed the calculation and I found these values, you can see. So K1, K2, K3 using the second equation, and these are the values we have got. And then finally we applied this formula to get WME, weighted mean error, and we got it as 0.69%. Then we compared this 0.69% of WME with the table number 3 requirements, and if it is within limit, then we say that WME test is what? It is satisfactory. So this is all about today's presentation, and concluding this presentation, I must say that yes, this topic is very vast. It needs more and more time to explain you, because I also wanted to explain all the test individually which is performed during the metrological control, or you can say whenever model approval is happening for a gas meter. But actually, if I will explain all those tests, so it needs 2 more hours to make you understand that how what test will be performed, and what are the steps and what are the regulations for that. So but in some other presentation, definitely I will cover it. And we should be knowing that the this gas meter regulation, which is recently included in our rule, is very, very important for the accuracy, safety, durability, and legal compliance. And to maintain this, strict enforcement, periodic verification is required so that we can protect the consumer rights. And as we all know that this particular measuring instrument is basically associated with a particular substance, which is what? Which is conventional source of energy, limited in our this world. Okay, limited quantity is there. So we should conserve this energy. So for that, for doing that, this gas meter regulation can play a very important role to by performing the accurate measurement and maintaining the accuracy through our legal metrology division of India. And that's all from my side. Now I would like to request our respected Director Legal Metrology, sir.
Thank you, Pandey Saab. Thank you very much. It was a wonderful presentation, and I hope that the people will understand how the gas meter need to be tested, calibrated, and all. Thank you very much. What I would request you to kindly share me this PPT after this presentation is over, so that I can put it on the website of the department, jagograhakjago.gov.in/seminars. Anyone at any point of time can see this presentation, can understand what is the plan and how this testing can be done as per the international practices. So thank you very much. I would like to thank all the participants available over here, Dr. Pandey, Dikshit Saab, NIC team, which is managing this, and Ahmedabad RSL, which are basically looking after this whole job. Thank you very much. Thank you all. Bye. We will meet again next week on next Tuesday. So this PPT as well as this video will be available on our portal. Thank you. Thank you very much. Thank you all. Bye.
Thank you so much. Thank you so much. Have a nice day, sir. Thank you so much.
Thank you. Thank you.
Thank you so much.
Thank you.